This is Zhong from Carnegie Mellon University. I'm here to present EpoMemory, a prototyping method for designing and fabricating programmable shape-changing interfaces. Tangible media has revolutionized the way we interact with digital data. It offers a more natural and intuitive way of presenting information through shapes, haptics, and dynamic behaviors. With the integration of shape-changing ability, more ubiquitous and adaptive interactions can be achieved. For example, shape-changing interfaces can communicate dynamic or spatial information with programmable curved surfaces. They can augment users as on-demand, personalized wearables, or can be leveraged as context-adaptive physical inputs and outputs through actuation and deformation. The previous work on shape-changing interfaces has focused on two approaches. One is the electrical-based method, where microprocessors and motors are used to control shape change. The other is the materials-based method, where smart materials and digital fabrication tools are used to create transformative artifacts that can respond to physical stimuli. However, it is challenging to integrate soft, compliant, and customizable interfaces with the electrical-based method. While for smart material devices, they often have only two distinct shapes, so there is a lack of multi-state or temporal programmability. It is also challenging to program localized activation because the entire homogeneous device would respond to the stimuli. So, we propose a shape-changing interface prototyping toolbox that overcomes the challenges of local activation and programmability. The toolbox includes the multi-state shape memory achieved with off-the-shelf epoxy resin, a library of structure primitives to showcase the design space, different fabrication strategies associated with these structure primitives, and epoxies functional composites. The multi-state shape memory is achieved by controlling the epoxy's glass transition temperature, which is Tg. If we combine epoxies with different Tg, for example, Tg1 for the green epoxy bar, which is lower than the Tg2 for the purple epoxy bar, so only the green bar will change shape when the combined sample is heated to Tg1, and the purple bar can be triggered when the sample is further heated to Tg2. In this way, we can realize multiple states and sequential triggering. Next, we present different structure primitives to explore the design space of our method. First, planar primitives can be programmed to fold or unfold, which enables large deformation or motion. A two-layer flower is used to demonstrate the planar primitive and is fabricated with casting and laser cutting. By laminating the epoxies with two different Tgs, the flower can be triggered sequentially. In a 60 degrees Celsius hot water bath, the outer layer will unfold. When the water bath temperature is increased to 85 degrees Celsius, the inner layer will unfold. The second primitive is the line-based structure, which can achieve a locking mechanism with sequential motion. A self-tying knot is prototyped using epoxies with three different Tgs. The epoxy was programmed with the initial knot as its permanent shape, and it was untied manually in a hot water bath to the temporary straight shape. The locking process is demonstrated by heating the prototype sequentially from 60 to 70 to 85 degrees Celsius. For volumetric primitives, we use the 3D printing to fabricate a spherical shell. Since epoxy is a liquid before curing and it doesn't melt after curing, it cannot be printed by fused deposition modeling. Instead, we use embedded printing with the supporting bath to sustain the uncured epoxy's shape while it is curing. This video shows the printing process, where epoxy was extruded into the bath with a direct ink writing printer into the desired shape, in this case a well, and the support materials can be washed away with water to release the cured object. Beyond the structure primitives with different fabrication strategies, we further explored several functional composites of epoxy. Here, we incorporate magnetic particles into the shape memory epoxy to induce magnetic responsiveness. As illustrated in this figure, the composite is rigid under room temperature and does not deform with external magnetic fields. But when the epoxy is heated, the strap becomes soft and is bendable by a permanent magnet, and it can be locked in its deformed shape by cooling below its Tg. Therefore, the temporary shapes can be programmed with this magnetic responsiveness, and no manual manipulation is required. In addition to additive particles, epoxy can also be integrated with onboard circuits for sensing. In this case, with conductive fabric patches as the capacitive sensing buttons, the device can be used as both a gamepad when it is flat in Figure B, or as a wearable computing interface when wrapped around the human body in Figure C. Finally, we demonstrate several applications of our method. The first one is the interactive morphing toy. In this octopus example, the head and the tentacles are printed separately with epoxies with different Tgs. So in a 60 degrees Celsius water bath, only the octopus's head undergoes shape change or recovery, while the tentacles are activated at 85 degrees Celsius. The second application is a shape-changing input device that can change shapes between 3 functional modes. The device is designed with 2 parts with different triggering temperatures. So when it is heated to Tg1, only the lower black part in the center figure will undergo shape transformation, and the top part will deform when the temperature is increased to above Tg2. This gives us 3 configurations that can be implemented to be a planar controller, a wearable, and a one-handed controller. The 3 corresponding interactive modes provide adaptability in various contexts. This video is showing the first planar controller mode of our prototype. When the prototype is heated to Tg1 in an oven, it transforms into this wearable controller. When it is further heated to Tg2, it transforms from the second wearable mode to the third one-handed controller mode. Lastly, we try to use the epoxy composite to make everyday objects more interactive. We create an interactive window shutter consisting of an array of magnetic composite straps. The units are designed with a flat permanent shape, so the shutter is closed by default. The units opening and closing are controlled by a magnetic glove. Depending on how the user waves their hand above the shutter, selected units can be triggered and opened to varying patterns, and allow different amounts of light to shine in. Here we show a 4-unit prototype of our interactive window shutter. At room temperature, no magnetic response is expected due to the composite's high stiffness. After heated and softened, the prototype can be deformed with the magnetic glove, and then it can maintain the open state by cooling. The shutter can be automatically closed by heating it again. In summary, we present a method or a toolbox for prototyping multi-state shape-changing devices, which includes the programmable shape memory behavior, various structure primitives, fabrication strategies, and different functional composites. The shape-changing interfaces designed with our method can provide context-aware shapes and functions. We believe that our work can contribute to the integration of smart materials with tangible interfaces, which will make our living environment more responsive to human interactions. Finally, we would like to thank the agencies funding this research and the audience for your time watching the presentation. Thank you.